Welcome to Data Structures from the Ground Up. Today, we are looking at trees. Trees are very important for tasks such as searching or representing a file system. A tree is a data structure that is comprised of 0 or more nodes. Each node has a value and 0 or more children. A node at the top of the tree is known as the root node. Nodes with no children are known as terminal or leaf nodes. One interesting thing to note is that each node itself is a tree. Each node could be a root of an entire tree. Because of this, in code, you will often see a tree being represented as just a pointer to the root node of an entire tree. A binary search tree is a special type of tree. A binary tree is just a tree where each node has 2 or less children. A binary search tree is a tree where each node has a value greater than all the nodes to the left of the node and a value less than all the nodes to the right of that node. This diagram here is a binary search tree. In order to make a binary search tree, nodes must be inserted in a certain order. Starting with the root, the new node must determine if it is greater than or less than that node. If it is less, it compares itself to the left node. If it is greater, then it compares itself to the right node. If there is no node there, that becomes the home for our new node, and the tree remains a binary search tree. Now, what is the value of arranging data in a binary search tree instead of something simpler like an array? Well, like the name implies, a binary search tree is far superior to the array in terms of searching. These two data structures contain the same elements, but we only had to visit 4 nodes to find the number 44, but for the array we had to loop through the entire thing. This will only get worse as you add more elements. The average case for searching a binary search tree is O of log n, while an array is O of n. Now, one thing to note is it is possible to have a binary search tree that is no better than an array. If, for example, you start out with a binary tree and keep adding to it successively larger elements, you're going to have a tree that is just one long line, and searching this will be just O of n, just like a regular old array. There are certain algorithms designed to keep a binary search tree balanced, such as AVL trees and red-black trees, and I'll be visiting these algorithms in a future video. Now let's take a look at some Java code. I have defined a class here for a tree node. This implementation has an integer value and up to 2 children, making it a binary tree. The constructor just takes in an integer and sets the value of the node to that value. In code, we will represent a tree by pointing to a tree node that is selected to be the root node. To make it a binary search tree, we need to add the functionality for searching and inserting. We'll first start with inserting, because we need that to build a tree at all. I will return true if the insertion completed successfully, and false if it does not. This is totally optional. If you want to define the function as void, that will work as well. The only argument this function is going to take in is an integer value that is the value we are trying to insert into our tree. We have to handle 3 different cases. The case where the insertion value is equal to our node's value, the case where it is greater than our node's value, and the case where it is less than our node's value. I just have that as else here because if it's not equal or greater, it's going to be less. And let's start with equals. That will be the easiest case. If the insertion value is equal to our node's value, we just return false to indicate the insertion was not successful. There's no point in having a duplicate node. We just want to know whether or not a node is in our tree, so just having a bunch of duplicates is totally pointless for us. Now let's take a look at what we should do if the value is greater than our node. First, we should check to see if we have a right node at all with our current node. If we don't, we make a new node with the insertion value, and that becomes our node's new right node. If we already have a right node in our current node, we recursively pass the insertion value to that node to be inserted. This way, the value will traverse down the tree until it finds its home. If the value is less than our node, it is very similar to how we inserted a greater node, but instead we do it to our left. Basically, the value is passed down the tree until it finds its home, and then a new node is inserted. So now we know how to insert a node, we know how to build a tree, it's time to look at searching. We're going to define search as a Boolean function, where it will return true if our value is in the tree, and false if it is not. Like insertion, there are going to be 3 cases. The first and most obvious is if the value is equal to our node's value. If that's the case, we're just going to return true, because the value is obviously in our tree if our node is the value of the search value. If the search value is larger than our node's value, we will look to our right. If our right is null, then we return false, as the value is not in the tree. If the right node exists, then we recursively pass our search value to our right node for it to search. If the search value is less than our node's value, then we do the same thing, except it is done to our left node side. Now let's go and test our tree. I have defined a tree, a new binary tree, as a tree node with the value of 42. Now, as I said before, a tree can be defined as just a pointer to the root node. So this is going to be the root node of our entire binary search tree. So from here, we're going to just insert values. So we're going to insert all these values, and then we can just test out our search to see what it returns. And I think it's really cool how it's like, all you have to say is like binary tree insert, and it's going to do all of that checking, all of that traversing down the tree, finding where it's supposed to go, making a new node. It's like, just insert, and there you go. It's going to be in our binary search tree. So let's go ahead. I have here system print line, binary search tree, search for 4. Let's see what this returns. So I ran our search, and it came back false, as expected. 4 is not in our tree. So let's just try a value that we know to be in our tree. Let's try 32. So 32 returned true, as we do expect. Like 32 is in our tree. Let's try 33 just for completion. And yes, 33 returned true as well. This experiment is a little bit boring. I thought something that could be a little bit more interesting is doing a little experiment where we compare the performance of our binary search tree against searching through an array, just like looping through an array to see if we can find the value. So to do this, I'm going to have 2 static integers that are going to be counters that are going to increment every time a value is looked at. So like anytime you're like in the search of the binary search tree and it like looks at a value, it'll increment the tree one, and then in an array, it will increment the score of the array counter. So I'm going to define these as 2 static integers here. So we're going to have static int tree score equals 0, and then static int array score. So from here, what I'm going to do is I'm going to make an empty tree, and I'm going to make an empty array list, and then I'm going to just from the set of numbers, like the first 500 integers, so say like 0 to 499, I'm just going to keep adding random integers to our data structure, and then I will generate random numbers from the same set and do a search. So let's say I'll add 200 numbers from 0 to 500, and then let's search for, say, 20 numbers. Okay, so I have an array list of integers here, an empty array list named int array, and then I generate a random number using nextInt. If you add a value here, that's the upper bound, so it'll be 0 up until that number, so 0 through 499. You can also just use this with no value, and then it'll give you any integer value, but I kind of want to keep it constrained to like the first 500 numbers. And then I'm adding the randomly generated number to our array, so that's going to be the first value. And then our tree is going to get this random number, and that's going to be our root node. That's going to be our first node. So now we have a binary search tree that it just has this root node, and we're ready to go, and we're ready to just start inserting random numbers. Okay, so I have this for loop. It's just going to run for 200 times. I'm not actually using this I value at all, because each time I'm going to just generate a new random number, and it's either going to, well, it's both going to be added to the end of our integer array as well as into our binary search tree. Okay, so for our test here, I am now doing a second loop for 20 numbers. I'm going to just search both of them. Now, as I loop through my integer array, I'm going to check to see each one if the value of the random number is equal to the number in the array. And if it is, I'll just break. And each time I'm going to increment array score just to see how many lookups we need to do in our array. Now, to do something similar in our tree, I'm just going to do search for random number because it's like we don't need this loop or anything because like we've already defined search. But I'm going to need to do something to add to our tree score. So I'm going to go back to tree node. So I'm just going to go in here and do ++app.treescore. I don't actually know how this is going to go. Like I haven't run this experiment beforehand. We'll see what we get. So at the end of this, we're just going to do a print line of our two scores. So we'll do system.out.println array score, and then system.out.println tree score. And I don't know. I expect the tree score to be better, but I don't think it's going to be that dramatic. I think it'll be more further apart when we do more searches. So let's just take a look. Let's see how it goes. Okay, and this was actually pretty dramatic. So for our array score, it took 3,278 lookups compared to our tree, which took 199. And each time I run this, I should get a different value. So let's try running this again. Let's see how it goes. All right, yeah, so this time it's 3,568 to 210. So this is, quite a bit more than I would have expected, but it just goes to show like how much better searching a tree is compared to an array list. Another thing to think about is our tree is much better at handling things that are out of the tree, like things that are just not in our tree at all, compared to the array list, which like it's every time it searches for something that's not actually in the array list, it's gonna have to loop through the whole thing. Whereas like the array list, the tree, it really depends, but like it might only have to search for like 10% of the tree. So from here, let's try doing maybe 500 inserts here, and let's do like 50 lookups. Let's see how this goes. All right, so it took 14,620 lookups to do the search through the array list, and then only 585 for the tree. So I'm hoping you can see at this point like just how much better searching through the binary search tree is compared to an array. Now, anytime in programming, there are going to be trade-offs. Like anytime it's like significantly better at searching, what's the trade-off? Like how can it be this? And some things to think about is inserting is going to be much more complicated with the tree. Like it has to traverse through the tree. So it's going to be O of log n to insert a new value into our tree compared to our array list, which is just going to be O of 1. Like it's just inserting at the end. It's easy. Things like looking up like a certain value within an array list. Like say, I want to know what the 12th value is in the array list. You can just do like get 12 and it's just O of 1. Whereas like a tree, it's like that doesn't even make sense. Like there's no way to do that with a tree. But if you're using this data structure for its intended purpose, just always have the right tool for the job. And I think there are certain situations where a binary search tree is just going to be much better for your lookups compared to looping through an entire array. In this tutorial, we have learned what a tree is, what a binary search tree is, how to make it in Java, and then we did a little experiment comparing a binary search tree to an array. I hope this video was very informative. If you have any questions or video suggestions, feel free to leave them in the comments. And that's all I have. I hope you have a great day, and thank you for watching.